is equal to BC. AC is equal to BC. Now, so it is enough to show that this is exactly passing to the midpoint. C is the midpoint of AB. Therefore, C is midpoint of AB. So that information is clear to us. But that is not enough, because we need to prove that it is a perpendicular bisector. Although it is passing through midpoint, it is a bisector, but we still don't know that it is a perpendicular bisector. And to do that, as these two triangles are equal, angle PCA should be equal to angle PCB. PCA, that means this angle, and PCB, these triangles are equal, and these two will form a linear pair. You know, for linear pair, the sum of the angles is 180 degrees. If you take this angle as x, this is also x, so x plus x is equal to 180 degrees. So 2x is equal to 180, and we can say x is equal to 180 by 2, which is 90 degrees. X is equal to 180 by 2, which is 90 degrees. So this angle is 90 degrees as well as this angle is 90 degrees. So we can say that these two lines are perpendicular. So we can say that this line is a perpendicular bisector. So this line is a perpendicular bisector. So therefore we can say that PQ, the line PQ, is the perpendicular bisector of AB. Once again, let's try to discuss about this question. First, we have taken PAQ and PBQ triangles, and we proved that these two are congruent using whatever the relations we are having. Side and side, and the common side, all the three sides are same. Right, so these are congruent, and from that congruency, we proved that these two angles are equal. So once these two angles are equal, we consider these two triangles PAC and PCB or PBC. We proved that these two triangles are again congruent. From that information, we showed that AC is equal to BC, as well as these triangles are also equal and equal to 90 degrees. So therefore, we can say that line PQ is the perpendicular bisector of AB. PQ is the perpendicular bisector of AB, right? So moving ahead, from the given figure, show that the line PQ, the same thing. Okay, we are done with this. The next question. In the given figure, AB and CD are intersecting at O. OA is equal to OB and OD equal to OC. Show that. So these two things we need to show. Let's try to understand what is the figure first of all. In the given figure, AB and CD are intersecting at O. Okay. So AB and CD are intersecting at O. OA is equal to OB. OA is equal to OB. This information is given for us. And OD is equal to OC. OD is equal to OC. So that means it was given that when you're comparing these two triangles, already two sides are same. So to prove that these two triangles are congruent, whether we need to have three sides common or two sides and one angle. SAS property, SAS congruency, correct? So carefully observe what else information is given to us. In the given figure, AB and CD are intersecting at O. OA is equal to OB. OA is equal to OB, and OD is equal to OC. Show that. So these two things. Now, carefully observe here. We need to take one more angle as the same. So these two are the angles. These two angles, okay, which we say vertically opposite angles. You know that, right? Angle COB is equal to angle AOD. These two are equal because these two are vertically opposite angles. Vertically opposite. Then there is no necessary condition that the line should be parallel or perpendicular. Always, these two angles will always be equal. We say them as vertically opposite angles. Okay. So now you can say that this one side is common to this side. This side is common to this side, and we have an angle A. So using SAS property, using SAS congruence, I can say that triangle AOD is congruent to triangle BOC. Right? Okay. So now, as these two are congruent, I can say that there are two angles which are equal. Angle OAD and angle BOC. As these two triangles are congruent, I can say that angle OAD is equal to angle OBC. Angle OBC. So as these two angles are the same, I can say that these two lines BC and AD are parallel. These are called these are called interior angles, right? Interior opposite angles. Okay, so these two angles are equal, so we can say that therefore BC is parallel to AD. Therefore we can say that BC is parallel to AD. So that is how you can use relations using the congruency of triangles. And you should be very careful in bringing the congruency, because you should maintain the same order. The corresponding side to side, angle to angle, you need to be very careful, or else you'll be doing mistakes in taking the different representations and wrong calculations. Okay, so let's move ahead. So next one is ASA congruency. ASA, angle, side and angle. Angle, side and angle. Okay, so the two triangles are congruent if two angles and the included, this is very important, the name included is very important, and the included side, angle and the included side of a triangle are equal to two angles and the included side of the other triangle, right? So let's try to take two triangles. Let's say these two angles are the same, equal to those two in the other triangle. Two angles and the included side. Included side means this side, not these two sides. Included means between these two angles with these two, we get this line segment, this side. So once these two angles and this side is equal, we can say that the complete triangles are in congruency. These two triangles are congruent. Alright. So let's try to have some discussion based on this one. In the given figure, AB is parallel to DC. AB is parallel to DC. Okay, what is AB? AB is parallel to DC. Okay, that I'm just saying that these two are parallel. Okay. Next, AD is parallel to BC. AD, that means this line and this line. Simply, it's like parallelogram. Parallelogram. Okay, where opposite sides are parallel. So now we need to show that triangle ABC and triangle CDA. ABC and CDA these two are congruent. Now carefully observe. If you consider AC as a transversal for these two parallel lines, okay, let AC, not let, it is a transversal, okay. AC is transversal for AB and CD, because these two are parallel lines. So from there what I can say, this angle and this angle are equal, right? Interior angles, interior opposite angles, correct? So we know that angle DCA is equal to angle BAC or angle CAB, right? Angle DCA is equal to angle CBA, angle CAB, right? So these two are equal. Now what we can say, see, these two lines, it was given that these two are parallel. From there we brought this angle and this angle is equal. In the same way, this angle and this angle are also equal, because the same property again, right? So once again we can say that because AD and CB are also parallel, so using the same transversal condition we can say that these two angles are equal. Which two angles? Angle DAC and an angle ACB. So now what I can say, this angle is equal to this one, this angle is equal to this one, and the common side is there, which is AC. AC is equal to AC, so it is angle side angle. So it is like a ASA relation, right? So we can say that using ASA relation, these two triangles are congruent. So we showed that sorry, therefore triangle ABC is congruent to triangle CDA. Triangle ABC is congruent to triangle CDA, right? So this is how you can try to formulate and try to use the congruency relations to prove many geometrical approaches, okay, or applications. Moving forward, line segment AB is parallel to another line segment CD. O is the midpoint of AC. The same thing, right? We have just discussed. So yeah, so let's move forward. AD and BC are equal and perpendicular to a line segment AB show that CD bisects AB. So what information we are having? Once again, sorry. AD and BC are equal. So AD and BC are equal and perpendiculars to a line segment AB. That means these two lines are perpendicular to AB. So this angle and this angle are equal. That is what he is saying. Okay. Next, show that CD bisects AB. CD bisects AB. Okay, so CD bisects AB. So let's try to understand more clear about that. That means O should be the midpoint of BA. O should be the midpoint of BA, right? CD is bisecting. Simply, we need to show that OB is equal to OA. Finally, to say that it's a bisector, we need to prove that OB is equal to OA. Okay, so for that we need to use the congruence of triangles, but still we cannot directly use that, right? We need some relation like SSS or ASA or SAS, whatever we have discussed. So now, as these two are parallel to the same, perpendicular, these two lines are perpendicular. One more thing we can discuss, this angle and this angle are equal because these two are vertically opposite angles. You can say that angle BOC is equal to angle AOD. Angle AOD, right? These two are vertically opposite. These two are vertically opposite. But using this information, we still can't prove that these two triangles are congruent. Okay, although you have a side equal, angle equal, one more angle also equal, but still we cannot say that because in SAS or ASA property, AA inside between the two angles, whatever the side you are getting, so that side, corresponding side should be taken care. Okay, so now what else we can do? So some of the angles of triangle is 180, you know that, right? Let's say this is 90, correct? This is X, this is X, and let's say this is Y and some Z. We still don't know about Y and Z, either are they equal or not. Okay, so in this triangle OAD, I know some of the angles is 180 degrees. So X plus Y plus 90 should be equal to 180. So X plus Y is equal to 180 minus 90 is 90. X plus Y is equal to 180 minus 90 is 90, right? So now, what is Y? Y is equal to 90 minus X. Y is 90 minus X. In the same way, let's try to relate there. Let's try to relate in that triangle OBC. In triangle OBC, same way, X plus 90 plus Z is equal to 180. Take that 90 other side. So X plus Z is equal to 180 minus 90 is 90. So Z is equal to 90 minus X. So these two Y and Z are equal. So I can say that. Okay. So Y, and I can also write the same thing as Y. Okay. Y is equal to 180 minus X. Or I can write like this. Angle ODA is equal to angle OCB. Now what I can say, side is equal, this angle is equal, and this angle is also equal. So ASA property, using angle side angle property, I can say that these two triangles are congruent. These two triangles, triangle OAD is congruent to triangle OBC. Is congruent to triangle OBC. Now, as these two angles are equal, we can still go ahead. As these two triangles are congruent, I can say that OB and OA. OB is equal to OA. So this is enough to show that CD is bisecting AB. CD is bisecting AB, right? So this is all the applications of different properties or different congruence relations that we have discussed in the last class as well as in today's class. Okay, so we have a couple of more applications based on like this. So one more question so that you can try. In the next class we'll be continuing with this question. L and M are two parallel lines intersected by another pair of parallel lines P and Q. L and M are two parallel and P and Q are also parallel. Show that triangle ABC and triangle CDA, these two triangles are congruent. So that we are going to discuss in the coming class, right? So I hope you understood all the things, all the relations which we have discussed in the present class as well as in the previous class. We'll be having few more congruences like this and more applications in the coming lecture, right? So thank you so much, friends. Stay tuned to get the next lecture. Thank you.
Hello everyone, so today we'll be discussing about law of conservation of linear momentum. Okay, so my name is Seshan Reddy, I'm a graduate from IIT NEET. Let's go into that. So first of all, let us revise what momentum is. Right, so what is momentum, everyone? How do we define momentum? Momentum is a very simple quantity. Momentum is nothing but the product of mass and velocity. Momentum is a product of mass and velocity. And some main points regarding momentum. Momentum is a vector quantity. Momentum is what? Momentum is a vector quantity and the direction of momentum is same as that of velocity. Right? Direction is same as that of velocity. Is same as that of velocity. Now what does this mean? I mean, I'll take an example. Let's say that we have a body, any object. Okay, we have an object that is traveling towards right, and let's say the velocity will be towards right. So if the velocity is towards right, in which direction will the momentum be? Momentum will also be towards right. So an object traveling towards right, velocity is towards right, and momentum is also towards right. That's what I mean when I say direction is same as that of velocity. Clear? So momentum is equal to mass into velocity. And another important point, what is the SI unit? SI unit will be for mass kilogram, for velocity meter per second. So it is kilogram meter per second. Is that clear? Okay, so these are some basic points regarding momentum. And obviously when we go into Newton's second law, it relates force and rate of change in momentum. Okay, that's fine. Now there is one basic law of nature, and that law is called as law of conservation of momentum. It is called as what? Law of conservation of momentum. It is applicable in many cases, but one of the simplest cases, one of the basic cases is when two bodies collide. You can see an animation here. You have a blue colored object and a red colored object. They collide and again they go in opposite directions. So using this law, or using conservation of momentum, we can find out after collision with what speeds will they travel and in which directions will they move. Yes, here you can clearly see before collision and after collision. So that's what we will be doing. In fact, there will be three cases: before collision, during collision, and after collision. We are mostly concerned with what are the velocities before collision and what are the velocities after collision. We'll go into them one by one and then you'll understand the case easily. Okay, good. And let me tell you, if we use this conservation of momentum, and when you are playing carom boards, right, you can easily predict in which direction the coins will fly off and with what speeds will they fly off. It is possible. It might be complex, but it is possible using what? Using conservation of momentum. So whenever the two bodies collide, that's when we talk about conservation of momentum in the simplest example. There are many more complex examples where conservation of momentum will be applicable, but for us, we'll be discussing about this case when two objects collide. When two objects collide. Okay, let's go into that. And as I told you, there is three cases that we need to be careful about. What are they? Just a minute. Three cases are, one is before collision, one is before collision, one is during collision, and the other is after collision. Okay. Now there will be a derivation. In that derivation we'll be going into these three cases, and once the derivation is done, once we get the result will only depend on these two. The result will depend only on these two, but the derivation will depend on all these three. Okay, we'll go into these cases one by one. Okay, and the derivation is important. So please pay attention, please be careful. Okay, so what we will do is we'll take an example of a case where you have these two objects. Let's say there is a mass m1, there is a mass m2, velocities u1 and u2. This is before collision. So before collision, in the sense m1 will go and will collide with m2. That means, for example, I'll say m2, if I take its speed as 10 meter per second, the speed of m1 will be greater than 10 meter per second. So start imagining, because m1 has to go and collide with m2. m1 has to go and hit m2. m1 has to go and hit m2. That means the speed of m1 should be greater, and the speed of m1 will be greater. Let's say it is 15 meter per second. Okay, so what the case that we are discussing is this. Let's say there are two objects. Both are moving in the same direction. Right, so the object behind it comes and hits it. And after it hits, what happened? Both of them separate and again they go forward. That's what we are discussing about. Okay, so whose speed should be greater initially? The object behind, right? The m1 is behind m2, so m1 speed should be greater, so that m1 will go and hit m2. That is the case that we are discussing about. This is the initial case, yes. So here, if I talk about momentum, right? If I talk about momentum here, what is momentum of object 1? We know that momentum is equal to mass into velocity. So here, for this object, mass is m1, initial velocity is u1. So we will say the initial momentum of object 1 is m1 u1. What about object m2? What about object m2? What is the momentum of m2? Say mass is m2, velocity is u2. So it will be m2 u2. Yes or no? And in fact, which momentum are we talking about? We have different cases. So we are talking about initial momentum. Now if I talk about total initial momentum. Total initial momentum. What is that going to be? Total initial momentum, you just directly add them. If you will say it as m1 u1 plus m2 u2. That's it. That is the total initial momentum. When I say total, it is of the two bodies combined, of the two objects combined. m1 u1 plus m2 u2. Simple? Clear? Good. Let's continue. So that's what we have discussed here. Initial momentum of object 1, m1 u1 of object 2, m2 u2. Total initial momentum of both objects m1 u1 plus m2 u2. So all the steps that we will be discussing will be written. You can go through them. Okay. Then this case is during collision. So what happens during collision, everyone? During collision, the objects exert or apply force on each other. This is m1, this is m2. Right, so what is F12? What does F12 mean? F12 will mean what? First comes on, second comes by, so force on object 1 by 2. I'll just say force on 1 by 2. And what does F21 mean? Again, the same naming convention, right? First comes on, so force on 2. Then comes by, so force on 2 by 1. So you have F12 and you have F21, two different forces. Clear? Pretty simple? Good enough. Now, on M1, which force is acting? F12. On M2, which force is acting? F21. Is that understood? So if I just take them separate, if I say M1, then on M1 the force acting is F12, and who is applying it? M2, and on M2 the force applied is F21. That is what's happening. So during collision, what happens? Forces act on M1 and M2. And when forces act, what happens? Velocity changes. Velocity of M1 and M2. On M1, F12 is acting. So M1's velocity will change. On M2, F21 is acting. So M2's velocity will change. So both their velocities change during collision because the forces are acting. Is that clear? Good. Next. So you can see clearly, and F12 is equal to minus F21. Why? Because Newton's third law, they will be equal and they will be opposite. Very important step for the derivation. They will be equal and they will be opposite. That means if F12 here was 9 Newton, here F21 will be how much? 9 Newton. They will be equal and opposite. That is the reason. Got it? Newton's third law. And you can clearly see they are opposite in direction. One is towards left and the other is towards right. Good? Okay. Then again let's continue. Let's go on further. Now the final case, that is after collision. Now we'll discuss about the case which is after collision. Obviously you can see during collision velocity has changed. So after collision, let's say the velocity of the object 1 is V1. Object 1 or of mass M1 is V1, of mass M2 is V2. So here we talk about which momentum? We'll call them as final momentum. We'll call them as what? Final momentum. And here you can clearly see for M1, what is the final momentum? M1, velocity is V1, so it is M1 V1. For mass M2, velocity is V2, so it is M2 V2. Simple? The final momentum M1 V1 and M2 V2. Then we talk about total final momentum. Total final momentum, right? What about total final momentum? You add them. So it will be what? M1 V1 plus M2 V2. Got it? Good, simple. Now think about this case. Imagine what's happening. Two bodies, the object that is behind was moving with greater speed, so it came and hit it. During collision, forces act and the velocities change. What happens? What happens is after collision, the remote will be going with a greater speed.